Introduction to Molecular Kinetic Energy. In this lesson, you will be able to derive an expression for the mean translational kinetic energy of gas molecules, relate the mean molecular translational kinetic energy and temperature, derive and use the formula for root mean square RMS speed of gas molecules, draw the graphs to show the molecular speed of distribution and interpret the shape of the graph, and predict the variation of molecular speed distribution with temperature. The animation shows 5 gas molecules moving in random motion inside a container. Click Freeze to freeze the motion of the molecules. Click on each molecule inside the container to know its kinetic energy. Now, click Total Kinetic Energy. Relationship between the mean translational kinetic energy of the gas molecules and the temperature of the gas. Observe the motion of 4 gas molecules in a container. Click Freeze to note the speeds of the molecules at a particular instant. Calculate the mean speed and the RMS speed of the 4 molecules. Click Check to check your answer. In this worked example, we are using the expression the mean translational kinetic energy of one molecule equals half m times mean square of speed c, which equals 3 over 2 times kT. Summary. The mean translation. In this worked example, we are using the expression the mean translational kinetic energy of one molecule equals half m times mean square of speed c, which equals 3 over 2 times kT. Summary. The mean translational kinetic energy of a gas molecule at temperature T equals half m times mean square of speed c, which equals 3 over 2 times kT. RMS speed equals square root of mean square of speed c, which equals square root of 3 times kT over m. Molecules in a gas move randomly with different speeds. Click on the yellow button to highlight the molecules moving within the lowest range of speed. How many molecules are moving within this range of speed? Answer: 3. Continue to highlight the molecules moving within different speed ranges. Which speed has the highest number of molecules? Answer: the blue speed range has the highest number of molecules. The distribution of molecular speeds in a gas is represented by a Maxwell-Boltzmann curve. Notice that the graph is not symmetrical. The lowest possible speed is 0, whilst the maximum is infinity. Click V0, V-mean and VRMS to see how V0, V-mean and VRMS are related. Click on the shaded area under the curve. What does this area represent? Answer: the area under the Maxwell-Boltzmann speed distribution curve represents the number of molecules with speed between V and V plus delta V. What does the area under the curve represent? Answer: The area under the curve represents the total number of molecules in the gas. Summary: the area under the molecular speed distribution curve represents the total number of molecules in the gas. Relationship between the three statistical speeds is V0 is less than V mean, which is less than V RMS. Click 300 Kelvin to observe the molecular speed distribution of the gas molecules at 300 Kelvin. Click 1000 Kelvin to observe the molecular speed distribution of the gas molecules at 1000 Kelvin. Describe the changes in the speed distribution. Answer: when the temperature increases, more molecules move with higher speeds. Since the total number of molecules remains the same at 24, this has the effect of lowering the height of the graph and shifting the peak towards higher speed. Click T1, T2 and T3 to see the effect of temperature on the molecular speed distribution. When the temperature increases, the speed of most molecules increase, the most probable speed increases, and the peak of the curve is lower. Since the total number of molecules remains constant, the area under the graph must remain the same. This means peak of the graph is lowered. The molecular speed distribution also depends on the mass of the molecules. Since RMS speed square root of mean square of speed c, which equals square root of 3 times kt over m, Vrms is proportional to square root of 1 over m. For molecules with smaller mass, the RMS speed Vrms is greater than the RMS speed of molecules with larger mass. Click buttons O2 and H2 to observe the molecular speed distribution for oxygen and hydrogen gas respectively. Summary: at higher temperature, the peak of the molecular speed distribution shifts to the right. The area under the molecular speed distribution curve represents the total number of molecules in the gas. At different temperatures, the area under the molecular speed distribution curve remains the same. This causes the peak of the curve to be lowered at higher temperatures.